induction. Now, before we start, let's understand a few terms. A few terms that you need to understand. First one. Magnetic flux. What is magnetic flux? You know magnetic field, and it is represented by field lines. So let's say we have a magnetic field. B. If I place a conductor, it can be a coil of wire, a metal plate, anything that has a surface area. I place it inside the field. This one, how many field lines we have in total? 1, 2, 3, 4. If I place it here, the two magnetic field lines pass through this area, or we say that the magnetic field line link to the area. This is the magnetic flux. Again, magnetic flux is magnetic field line linked to the area. So if I ask, what is the magnetic flux of this conductor? You will say 2. Out of 4, there are only 2 lines linked to the surface area. So the flux is 2. It has a symbol of 5. Okay, this one. Now, if I increase the area, let's say this is my first metal plate. What is the flux? 2. Okay, because only 2 lines link to the area. If I increase the area, what is the magnetic flux linked to this plate? 1, 2, 3, 4. So now your flux has increased to 4. Okay, so magnetic flux is just magnetic field line crossing the area. How many of them crossing the area? It is a measure of quantity. We are talking about quantity. So we will define here quantity of field link or crossing to the coil. Because usually you deal with coil, we just say coil. It can be any conductor, okay, or linked to the surface area. If I want to increase the magnetic flux, that's the first way I increase the area. The second way I can increase the magnetic flux. How do I increase the quantity of the line crossing or passing through the surface area? I can increase the number of lines. To increase the number of lines, you are increasing the magnetic field strength, right? But there's no such term. We call it what? Magnetic flux density. This one. If I increase the magnetic flux density, that means the field is stronger. Stronger, that means the lines are closer together. So you will have more lines. Increase the magnetic flux density. Again, you will increase the magnetic flux because there are more lines crossing the surface area. There are more quantity crossing the area. So you know magnetic flux depends on 2 things: area and magnetic flux density. So we'll derive the formula. This one, phi equals to dA. Okay, the higher the B, higher the A, this one will be higher. Now, all these lines is making 90 degrees with the plate. If I take the plate like this is the surface area, this is the areal vector. The areal vector is perpendicular to the surface area. Now, if I tilt the surface area like this, then the areal vector is making an angle with the magnetic flux, like this. Okay, so if I tilt the metal plate, this is the areal vector, then the field cross, they are making an angle. I can tilt this plate like this. Okay, this is the field like this, or I can tilt it side to side like this. Yeah. So I tilt it like this, it makes an angle, or side to side, it makes an angle. So general form for the formula, we just say BA, then we'll take cos whatever is the angle. So if you're perpendicular, then we just drop this one. Because cos 90, this one, left only BA. Okay. Now, unit, this is a vector, this is a scalar. So magnetic flux is a scalar because it's a quantity, right? We are talking about how many lines linked to this one. Scalar unit. What is the unit of magnetic flux? We call it Weber. This is Tesla. Tesla, this is Weber. What is Weber? Weber is Tesla into area, T into m squared. Weber is Tm squared. That means we also have another unit for the magnetic flux density. If I move like this, B equals to phi over area, this is Weber, WB, this is meter squared. That means this one, the unit can also be Weber per meter squared. Okay, so what is Weber per meter squared? It is Tesla. Same here. They are the different unit for magnetic flux density. Okay, so Tesla or Weber per meter squared. That is the unit of B. What is the unit of this one? Weber. Now, I change this to a coil. The coil is hollow in the middle. But how do we get the area? The area is still this one, even though the middle is hollow. But when we calculate the area linked to the flux, again, we will take the entire area of the coil. The coil can be many turns. It can be 1 turn, 2 turn, 3 turn. If it's only 1 turn, we will call it magnetic flux. That's it. How many quantity linked to this one? Okay, crossing the area. If you have n turns, 300 turns, 500 turns, then we will call it magnetic flux linkage. Okay, so magnetic flux linkage is actually the same as flux, just with multiple turns. And that is when we usually refer to solenoid. Solenoid. What is a solenoid? Solenoid is like a coil of wire with length. It is not a flat coil. It has a length. So if I change this conductor to a solenoid, then we get the magnetic field crossing it. This magnetic field can be from a magnet nearby, or it can be from another coil of wire that has current placed beside it. It's come from here. Then this linked to this, we call it magnetic flux linkage. What is the linkage of this one? The quantity of the flux linked to our solenoid. So that changes our equation. Saying we will add a quantity, number of turns, NBA plus theta. Okay, so let's say I want to calculate. All right, our coil has 100 turns. And then given the radius is 0.5 meter, the flux density B is 5.0 millitesla. What is the magnetic flux linkage? Okay, we just put in 100. 5 times 2 R squared, 0.5 squared. This is perpendicular, so we will drop this. Okay, we get how much? 0.39, is it? 0.39. Okay, unit 0.39. This is flux linkage. Flux linkage is, you got N here, you see, this one, the dA cos theta. This one is your flux. Sorry, I should write here, flux linkage. Flux linkage and flux, what is the relation? You just time the N, okay? So this is turn, this is Weber. So we write Weber turns. 0.39 Weber turns. Okay, now, this is just the basic. First, understand what is magnetic flux and what is magnetic flux linkage. Okay, now we go to the next part. We will apply, you will always see this term when we proceed. Now, in the electromagnetic induction, it all started from two experiments, and this is very important, two experiments. I will show you how they actually discovered this behavior of electricity and magnetism. Let's start with the first one. Faraday and Henry's experiment. Okay. Number one, experiment number one. What they did is they take a coil and then connect it to a meter. This is to measure whether there's current flowing or not in the coil. And then they take a magnet here and it's starting from a distance from the coil and slowly push close to it until here, stop. And then pull it back. Again, we separate this action into four parts. Start here, push close to it, stop, and then pull back. Now, notice that there's no power supply in the wire here. There's no power supply, there's no current. Just the wire or a conductor and the magnet. Rest when the magnet is at this position, number one. Rest. They observe, okay, what is the relation between the motion of the magnet and the deflection of the galvanometer? What is the relation there? At rest, the galvanometer reading shows 0. Start to move towards it. Okay, number 2. Moving towards. Moving towards. Here, they observe. They see a current is produced in this circuit. Then, moving towards, stop. Again, there's no current. And then, moving away. See, current, but in the negative direction. Right, so that is the observation. This experiment. Based on this observation, okay, they make a conclusion. They make their observation. What they see, whenever magnet is at rest, whenever magnet rests, there's no current. No current is produced. Whenever magnet is moving, current is produced. Okay. We haven't talked about why. This is just observation. Later we will talk about why, and you will need to explain why. In the questions, they always ask, for the explanations in this chapter. Okay, so understanding is very important in this chapter. Now, that is the observation from experiment 1. Very simple, straightforward. Let's look at experiment 2. Experiment 2 slightly different. They use, instead of a permanent magnet, they use a coil. Use another coil. Okay, this is the setup. One coil. This one is connected to a power supply. Coil. One. Second coil. No power supply. Now, this one we want to observe how the motion in relation with the current produced, right? This one we want to observe how closing and opening the switch affect the current produced in this circuit. Okay, let's see. How many stages? Let's divide it into 4 stages. When the switch is open, when the switch is closed, during the closing, the action of closing it. Okay, and then close, and then open. What they say is that when the switch is like this, open, there's no deflection in the galvanometer. And then when you close it, the action of closing, you see the deflection here. After you close the switch, this one again drop to 0. And when you open it, again you see the deflection, and then drop to 0. So the observation says that whenever you close the switch, there is a deflection, a temporary deflection in the needle. After you close it, this one will drop to 0, even though there is current flowing in this circuit. Okay, so we'll make here open circuit. When circuit is open. Okay, this one is open switch. Current in coil 1. Current. Switch is open. Is there any current flowing here? There's no current flowing here. 0. Here, again, there's no deflection. 0. Closing switch. When you close the switch, there is a increase in the current from 0 to a certain value. Okay, can be 0 ampere to, okay, say 5 ampere. The increase in the current from 0 to 5 here, then what do we see here? Again, current increase from 0 to 5. When the switch is closed, is there any current flowing in coil number 1 when the switch is closed? Yes, there's current flowing. So, but here we see this one is 0. And opening switch. This one, I drop to 0. And this one, 0. Again, increase to I. Okay, that is our observation. Based on here, they make their observation. Whenever, what happened here? At what situation when the current is 0? This one. Open switch, closed switch. What does it mean? Here, current is 0, current is I. Maintain at 0 or maintain at 5 ampere. That means we say there's no change in current. Here, 5 ampere flowing, remain 5 ampere. There's no change in the current. Here, 0, remain 0. There's no change in the current. So when there's no change, when no change in current, current is 0. in coil number 2. When there is change, in current. Doesn't matter increase or decrease. As long as your current is changing, then you will see current induced in coil number 2. Okay, so that is the Faraday's and Henry's experiment. Okay, based on this one, what can this tell us? And what conclusion is made based on these two observations? Comparing this one, at what condition when current is produced? The keyword here, whenever magnet rests, no current. Whenever magnet moving, current is produced. So we are talking about the change in motion. Motion of what? Motion of the magnet. Here is change in motion. That one is change in current. We must have change in current for the coil to read the current flow. Okay, so something to understand here. Current static, there's no current induced here. Only when closing or opening the switch, changing current, this one will increase. At what situation I can create change in current? This is one way, increasing or decreasing, opening or closing switch. The other way, I can use AC current. Because you know AC current, the graph is like a sinusoidal graph, that is a changing current. So if you change this battery to an AC current, then you will see the reading deflection over here. Okay, so two ways you can produce change in current. Change to AC or simply by opening and closing the switch. But that is just temporary. Now, why? Here we will answer why change in motion and change in current will have current over here. What's the reason? Okay, let's see. Example 2 first. We know that magnetic field is produced by two ways. Magnetic field. First is by magnet, permanent magnet. Second is by current carrying conductor. If you have a wire, current is flowing it, then you have magnetic field. Right? So two ways to produce it. In this experiment, do we have current? Okay. When the switch is open, we do not have current. Let's say I close the switch. When I close the switch, current increased from 0 ampere, 1 ampere, 2 ampere, 3, 4, 5 ampere. At 0 ampere, what is the magnetic field produced? The magnetic field produced is 0, produced by coil 1, because current is 0. 1 ampere, okay, there's magnetic field, right? But the magnetic field, think of it like, okay, this is like giving off its magnetic field, right? But what is the magnetic flux? Remember, magnetic flux is the field that link to the conductor, right? So if here, increase current to 1 ampere. Coil number 1 produce magnetic field, there is magnetic flux linkage to this one. So 1 ampere, 1 flux. Increase the current, more magnetic field, the quantity of the magnetic flux will increase. Linked to this one. 2 ampere equal 2 flux. 3 ampere equal 3 flux. 4 flux, 5 flux. Okay? So increasing current, the flux linked to this one increases. When there's increase in the flux to this one, we say what? There is a change in flux. Change in flux. The flux is increasing. It can be increased or decreased if I close the circuit. If I close it from 5 ampere, 4, 3, 2, 1. 5 flux, 4, 3, 2, 1. Change in flux. Who causes the change in flux? It is because of the change in current that causes the change in flux here. Okay, because current has magnetic field. Right. So I will write here, change in current causes change in flux. Please remember this keyword. Whenever you answer explanation questions in the electromagnetic induction, always talk about flux. Always. Change in flux. If I maintain the current at 5 ampere, when the switch is closed, here, 5 ampere. 5 ampere I maintain, then 5 flux is maintained. 5 flux is maintained, is there change in flux? There's no change in flux, it's 5 flux maintained. That's why here, you have no induced current. Okay, now, come to this one. Why change in motion will induce current? Same principle. When your magnet is at this position, how does the magnetic field look? North to south, right? North to south, north to south, north to south, like this. It's the magnetic field. At this position, what is the magnetic flux? 1, 2, 3, 4, 5 lines. The one that linked to this is 1, okay? 1 flux. At this position, 1 flux. Yeah? Now, I move this one to this position. 1, 2. From this position, simply by moving it to here, how many magnetic flux link to this one? 1, 2, 3, 4, 5. Okay, 5 flux. So when you are further out, the flux linkage is less than when you are closer here. There are more flux linkage. So again, moving this one here, you have a change in flux. Change in motion causes change in flux. Then EMF is induced. Current is induced. If I maintain this motion here, 5 flux, bring it here, stop here. Again, there's no change. 5 flux. Current is 0. Right. So similar case, these two. We arrive at why is current produced? Because there are change in flux in 2 experiments. So whenever we explain why current is induced, you always start by saying there is a change in flux. How many ways can we change the flux? Okay, we will discuss. How many ways the flux? Okay, we come to the flux formula. Phi equal VA cos theta. If I want to produce the change in this flux, what we discussed here, change in motion and change in current. That is just 2 of the many ways. VA data. First one, change data. By changing data, you change flux. That's it. Okay. By moving the plate in this magnetic field, you move the plate like this, like this. You are producing change in flux. Simply by moving plate, rotating the plate in the field, there's induced current. Change in angle. Number 2, change in area. How to make change in area? Okay, one example, and in this example, they like to ask also. Imagine that this is a field. How do you make change in area? This is the field. Okay, so X, that means the field is going towards the ball. I take a conductor, it can be a metal plate, anything. I hang by a string, and then I let it oscillate like this. Okay, now when this oscillates until here, this upper section has entered the field. So it has certain flux. It swings here, the overall entire area has entered the field. So your area changes. Your area has increased. Okay, from here, no area. Swing here, this one, area increase. So there is a change in area. You let it oscillate, change in area, then there is a change in flux here. So that is another way to induce EMF. Where is the EMF induced? The linkage is linked to this one. Because this is the field, this is your metal plate. The linkage is linked to this one. So there's a change in flux to this one. The EMF is induced in this object, this conductor. If I change this to insulator, is that EMF? No, it must be a conductor. Okay, any conductor. So not necessarily must be a coil of wire. It can be a plate. If you use a plate or an iron core, anything, then the EMF induced, we call it the eddy current. And I'll come to that later. Okay? Right, so that is just to give you an idea of how area change. Oscillation, like this. I bring it like this, area is changing. Yeah? Now, number 3. Change in area or change in the flux density. This is the example we did just now. This is change in flux density. The magnet is also change in flux density. How many ways? It can be the switch on off or AC current or magnet moving towards or away. Okay, so these are the ways that we can produce the change in magnetic flux. Right. So whenever you have change in magnetic flux, is current produced first or EMF first? EMF is, we say EMF is induced. Okay, change in flux, EMF is induced. What is EMF? Voltage, potential is induced. If I disconnect this circuit, this is not connected, and then I close this one, is there current in this field, in this circuit? When you close the switch, there's change in current, but still current is not produced in this circuit because you have an open circuit. So it must be a closed circuit. EMF is induced doesn't necessarily mean your current is induced if your circuit is an open circuit. So only when you close the circuit of the conductor that's being placed in the magnetic field. When EMF is induced, then only current is induced. So here, it must be a closed loop. If this is a closed loop, then current is induced. Right, Faraday's law. Now I will write out the definition of Faraday's law. Right, so based on the observation from experiment 1, 2, he made the law. This is based on the observation of the 2 experiments. He made this law 1, law 2. Okay, so it's a summary of what is happening just now. Law number 1, change in magnetic flux linked to a coil induce EMF across a coil if they are in a closed loop. So that explains the concept behind it. Law number 2 talks about the calculation behind it. If we want to calculate what is the amount of EMF induced, how do we calculate it? Okay, based on this. See, the EMF induced across the coil equal to the rate of change. The rate of change of the flux. Whenever you see rate of change is how much something changed when another variable changes by an extent. So oftentimes rate of change is referring to dt. How much something changed when the time changes. Okay, it's comparing between 2 variables. So the rate of change of the flux, that means it's d phi over dt. Now another way to think of it is like this. Here, we can write an equation. EMF is equal to the rate of change of the flux in the coil. So d phi over dt. But we have to put a negative in front here. This negative says that the EMF produced opposes the change, opposite to the change. Okay, what does it mean? The negative, okay, we'll save this for later. I'll explain this, why there's a negative. This is actually based on the second law, the Lenz's law. Faraday's law does not talk about this negative. Faraday's law is just like this. So in the exam, you can just write E proportional to d phi dt like this. It does not talk about direction or anything. This is from Lenz's law. Okay, so Lenz's law, we save it for later. Now, let's come back here. EMF can be calculated using this one. So what is rate of change of this one? Now think about it like this. Just now we say the coil like this, right? And then there's magnet, NS. At this distance, let's say the flux is 50. I bring it here, close to it, the flux increase to 100. How fast I bring it? I do this in 5 seconds. There is a change. How fast is the change in 5 seconds? That is rate of change. If I can do it in shorter time, 1 second, okay, that is higher rate of change. So you can think of it like speed. Has something to do with speed. So the rate of change of flux. How do we calculate the EMF produced in the coil here? If we move this one over here in 5 seconds, right? We can do it. Here, very simple, change in flux. What is the change? I only want magnitude. Magnitude only. That means I just take the bigger minus this one. 100 minus 50. Let's do 5 seconds. 50, 5, 10 volt. Okay, so here we can calculate 10 volt. Okay, but actually the EMF, it has a negative here because of this negative, right? But in the exam, it really doesn't matter. If you write 10 volt or negative 10 volt, they will still give you correct based on the answer scheme. Okay, so this is just magnitude. Now, EMF is calculated by rate of change of flux in the coil. That is Faraday's law. This formula, please remember, very, very important. And also this formula, from here we can derive many. Okay, like what? D phi. Remember phi is flux, right? Magnetic flux. If I have a solenoid, what do we call this? Magnetic flux linkage. If I have a solenoid. So we will change this E equals to negative D magnetic flux linkage and phi D dt. D and phi dt, okay, this one equals to negative D and dA. From here, we can also get, if let's say this is coil 2, it is a closed circuit. Okay. And here, this is coil 1. It is connected to power supply. Do a switch. The EMF produced in this coil, okay, this EMF is produced where? In coil number 2. Can be calculated by number of turn of coil number 2. B, whose B is this? This is the B from coil number 1. Okay, or any incoming field. That is the B. Area, whose area is this? This is the area of coil number 2. Coil number 2. Okay, and dt. Now, if I want to induce EMF on this solenoid, there are many ways I can do it, right? We have seen it. There are many ways to have a change in flux. You can change the angle, you can change the area, you can change the current. Many ways. So let's say here I change the current. I change the current by closing the switch. closing switch. By closing switch, you have a change in flux. Closing switch means I'm changing the B, this one. Change. Right? Because current affects the B. The larger the current, the larger will be the B. The B is what? Again, magnetic flux density. Just like gravitational field strength, but for magnetic field. Okay? How strong is the field? Depend on current. So by closing the switch, you are changing the B. Am I changing A and N? No, I'm not changing, because this remain as coil 2, remain as the area. The turn remain the same number of turns. I'm not changing anything. So that means this is a constant, this is a constant. This is a constant, this is a constant. In this case. Right? So here I will write like this. E equals to minus constant, I can bring it up. NA and then dB dt. Because I'm changing the flux by adjusting, closing the switch. I'm changing this. This I'm not changing. It is a constant. I will bring it up like this. So from here, we get E is proportional to dB over dt. Please remember this relation. This is the first one. No, actually, this is the second one. The first one is this one. d phi dt. EMF is proportional to d phi dt. This is EMF is proportional to dB over dt. Okay, there's one more. Let me mark this down. 1, 2. There's one more. From here, B, we know that it is dependent by current. The larger is your current, the stronger is the field it produces. So we write B is proportional to current. Larger I, larger B. So B is proportional to I. Okay, then what can we do? B is proportional to I. Here it says EMF is proportional to rate of change of B. B is proportional to I. That means I can change this to current also. I can also write E proportional to di over dt. This is the third one. Okay, here. Let's do it. Again, general, come to here, bring out the constant, and get the relation with the magnetic flux density. Since magnetic flux density also proportional to current, we can also say EMF is proportional to rate of change of current. So you get these three relations. Let me write it here. This is for the graph part. Okay, the relation with all this. If they want you to calculate the exact value of the EMF, we can straight away use the equation to calculate the exact EMF. That means you have to put the number of turns, the area, and then the change of this one at the time. But sometimes, most of the time, they ask you to do graph. And graph is always related to these three equations. Okay, so okay, they cannot see this. Let me bring this in. So they can give you three types of graph, phi, t. That's the first one. They can give you current, t. It can also give you B against T. Here. Let's say B against T. Graph looks like this. Then they say, what is the EMF from 0 to 2 seconds? Here you have a graph of B against T, this relation with the EMF. That means the gradient of this graph, if I calculate the gradient of this graph, m dB over dt, this one is this is the gradient of. So EMF is proportional to the gradient of the bt graph. Okay, EMF is proportional to the gradient of the bt graph. And this part is where they like to test it. They ask you find EMF from the graph, calculate EMF, they ask you plot the graph, and you have 3 of this. We will try the questions, okay? Now, if I put, because this one actually you got a negative here, right? Because of the Lenz's law. EMF, the equation has a negative here. That means if your gradient is a positive, then the EMF, it should be a negative. Because EMF opposes the change in the flux. If your gradient is a negative, then your EMF will be a positive. From 0 to 2 seconds, this is constant gradient. So if it's constant gradient, your EMF is constant because proportional, right? This is constant, this is constant. So you can expect how does your graph look like if you were to plot EMF against T. If you were to plot EMF against T from 0 to 2 seconds, you will get like a horizontal line. Because this is a constant gradient, your relation is that one. This will be a constant value. This is a 0 gradient, horizontal line, 0 gradient. So gradient of this is proportional to EMF. This is 0. Okay. Now this is positive, right? So I can actually bring this down to negative. Negative constant. Positive gradient, negative EMF. Negative EMF, positive, sorry. Negative gradient, positive EMF. So that is your graph of EMF. If you want to change this to this one. Okay, am I going too fast? Okay, try question 1, 3, and 5. 1, 3, 5 first, the rest later. I'll send it in the group. You can check your answers at the back. Ada man. and how high. And then the height is the height of this one because the gradient is back, gradient is more. Okay. Right. Look at number 1. Okay, we have IT graph, E proportional to dIdt. So EMF is proportional to the gradient of the graph. Now, remember, not equal, it is proportional to gradient of graph. That means the gradient of the graph is not the EMF, it's just proportional to it because this is times into a constant. Remember our n, there's formula inside also, right? The constant value, okay, NA, right? Okay, again, this is proportional but not equal. They're not the same, huh? Okay, number 1, state Faraday's law of electromagnetic induction. Okay, induced EMF is directly proportional to the rate of change of magnetic flux linkage. So you give this one E is proportional to D and phi dt. Question 1, guys. For the online students, we are at question 1. Okay, number 2. Now you're given a EMF time graph. On the axis, sketch a graph to show variation of time of the EMF induced in a small coil. So you want to look at the gradient of the T1 and T2. Now look carefully, the grid T1 is the gradient the same, T1 and T2. Look at the line. No need to calculate the exact gradient, just compare T1 and T2. Notice that T1, it takes 2 boxes. Here's the graph. IT. At T1, the line takes 2 boxes like this. And then if you compare to T2, this one takes half a box. Sorry, this one should be half a box, half a box. So which gradient is bigger? Is it T1 or T2? The gradient. You check the grid. Look carefully the grid. T2. It is from the steep line down, right? The steep line down, it started from half the box to half the box. That means T2, there's only 1 square. 1 square. This has 2 square. So which one gradient is bigger? This one is bigger than this one. M2 is bigger than M1. Gradient is not the same for these two. Okay, so this one is 2 boxes. This one is 1 box. So the gradient of 2 is twice the gradient of M1. You can do it like this. Okay, they have the same height, right? They have the same height. Okay, let's put some value, random value, because we are just comparing these two. We put 1. Gradient at 1 is y over x, 1 over 2 squared. Gradient at 2, m2 is 1 over 1 squared. Okay, then you just divide up, and 1 over m2, 1 over 2, and 2 m1 equals to m2. Gradient at 2 is twice the gradient of 1. So that means your graph on the EMF, the T2 should be twice the height. Okay, the T2 should be twice the height. This is your T1. You draw it like, okay, it's a negative, right? It's a negative, so we do T1. From where it starts, the rectangular box from where it starts, 1 squared before T1 and 1 squared after T1. So you're going to draw a straight horizontal line 0 all the way to 1 box before T1, same as the IT graph. Just like how they did. 1 box before T1, then draw this rectangular box that takes 2 squares. Doesn't matter what is the value here, because we're not finding the exact EMF. We cannot find the exact EMF. This is just a proportional relation. The exact EMF is the gradient multiplied into some constant. Okay, but here, we just draw it to any height will do. Doesn't matter. We just want to check the time here. Okay, now and then draw a horizontal line all the way to T2. All the way to where? Half a box before T2. Half a box before T2. And then the width of this rectangular block is just 1 square. This one is 2 square. The height should be twice of this one, because the gradient is 2 times. So this one. And starting here, it's flat. Okay, so B. The small coil in A is now replaced by a Hall probe. Okay, now you want to recall back your Hall probe lesson. Hall probe is positioned so that the reading for the probe is a maximum. What does this sentence mean? It means that the probe is adjusted so that it is 90 degrees with the magnetic field. That is where you get maximum reading. The current I in the solenoid varies again as in the figure. On the axis, sketch a graph to show the variation of time of the reading VH. So that is the Hall voltage, right? Now, if you change the coil to a Hall probe, okay, that's your Hall probe. What's the formula related to our Hall probe? There's just one, right? VH equals to by net. By net. That's the Hall voltage formula. So imagine I change the coil to Hall probe. Then, from this formula, we use the same Hall probe, right? We move the Hall probe inside. It's the same Hall probe. That means I, N, E, T, they are all the same. I, N, E, T, they are all the same. Same Hall probe. Huh? So VH is proportional to B. VH proportional to B, and also we know B is proportional to I. Again, where does this come from? This is the current and magnetic field. The larger the current, the larger will be its magnetic field. So B is proportional to I. This relation. V proportional to B, B proportional to I, VH proportional to I. Okay, this one tells us our VH graph is proportional to our IT graph. That means they have the same shape. They have the exact same shape. So you draw your VH graph, same as your IT graph. But the value is not the same, right? It doesn't matter, you can draw it to any value here. The value is not important, we just want the shape. Okay, question 3. Magnetic flux linkage, all right? You can just give the formula. Flux. The product of B and A. Okay, question 3b. A solenoid of diameter 6 cm and 540 turns is placed in a uniform field. Okay, so that's the graph. Now, again, you are given what graph is that? Flux density graph. That's the B against T. What's the relation? EMF proportional to dB. If I want to write the exact equation, this is minus N equals to minus D and Y. Okay, so this is the exact equation. Calculate the maximum magnitude of the induced electromotive force, so the EMF. Then they want the maximum. So we use this equation. They want the exact EMF, right? So we're going to use the actual equation here. Negative. Number of turns. Okay, we have all the parameters. But then the dE dt, you're going to find the gradient at the back, because that is the greatest gradient. That is the highest gradient. They want the maximum EMF. should be a negative here. This is negative green. Okay, C. So a copper sheet is put between the magnet and then allowed to oscillate. And then you got two copper sheet, X and Y. Y is the one that is cut out. Okay, it's like they have like a comb shape. Okay, two copper sheet is allowed to oscillate in between the magnets, and that is the graph you get. Displacement against time. Okay, let's look at the question. State the name of the phenomenon illustrated by the gradual reduction in amplitude. That's damping. Okay, reduction in energy. This is in oscillation. C number one. Damping. Okay, the reduction in the amplitude of the dashed line. But then the solid line, there's no reduction. Then they ask, okay, deduce which copper sheet is represented by the dashed line. Is it X is the dashed line or is it Y is the dashed line? Explain your answer using principles of electromagnetic induction. Whenever you see they ask explain the principle of electromagnetic induction, always start with flux. Okay, number two. How do you explain this one? Questions, So talk about flux first. Is there change in flux? This one is an example. We've discussed it just now, right? The oscillation one. Change in area. When you oscillate the copper sheet in the magnetic field, there's a change in area. Change in area causes change in flux. Number one, change in flux causes induced EMF. One mark. The sequence always goes like this, fixed. Change in flux causes induced EMF. Then the second one, what happened next? Induced EMF causes current. But is this a coil of wire? It's not a wire, right? It's a metal plate. So is there current induced? There is still current induced. Why? Whenever you have a conductor in the field, okay, so let's say like this. This is the magnetic field. It can be from a magnet, from a current, anything. I put a coil inside. There is a linkage. The change in the linkage induces EMF and current in the coil, in the solenoid. If I put a plate, a conductor, both are conductor. Conductor, they have free electrons. So if I put the plate here, when there's a change in flux, there's again induced EMF and induced current. Same. Not only happen in wire, in conductor as well. It will induce current in this conductor. But this current, we call them eddy currents. Like small, tiny little currents over here. Because current is just flow of electrons. When you put the metal plate in the field, change in flux causes the electron to move also. It causes all the free electrons in the conductor to move. And this is what creates eddy current. Okay? Here, induced current, eddy current. Eddy current, is it good or bad? Eddy current will cause heating in the conductor. It will heat up this one. Because you have current, current causes heating. Just like if you take a solenoid. You take a solenoid. When you take another solenoid, connect to power supply, and then you have the field like this. Right? This one with power supply, this one don't have power supply. So the change in magnetic flux, let's say I make it AC. So this flux is changing, right? If it's AC, current goes in this direction, the other direction, the flux is changing, and it causes change in flux to this one. Now, the EMF or the current induced in two of the conductors. You have EMF induced in the wire, the current in the wire. You also have EMF or current induced in this iron core, Okay. You also have current induced in the iron core. Together, this one and this one. Okay. So the current induced in the core, we call it eddy current. The current induced in the wire, you can measure it, right? But the current induced in the core, eddy current, and this is what causes the heating of the iron core. And heating causes loss of energy. Okay, whenever you have heat, you have loss of energy. Right. So in this example, they take a copper sheet in the magnetic field, right? They let it oscillate. So that will induce EMF, and then the EMF will induce current inside the copper sheet. Inside the copper sheet. So we'll write here the induced EMF. Induced EMF causes eddy currents. Sheet. Okay, now next one. Eddy current in the sheet causes what? Heating, right? Heating. Okay, so the eddy current causes heating and energy loss. So dissipates energy. Comparing the two plates, one is like this, another one is cut out like this. Why we make a cut like this? Because when there's no cut, electron can easily flow around. They can do this, they can do this. Electron can easily move from one location to another one. If I make a cut like this electron, they cannot cross. They cannot cross here, cannot cross here. If I make more cuts, it makes it more difficult for the electron to flow. If it's more difficult for the electron to flow, then your eddy current will decrease, because eddy current is just the flow of electrons. So how do I decrease the eddy currents? I'll make a cut. I put gaps in the conductors, preventing the electron to flow. This one, you have a smaller current, smaller eddy current. This one, you have a larger eddy current. This is plate Y, this plate X. So which graph is the dash one? The dash one, you see the displacement decreasing. That means energy loss. Which one has higher energy loss? This is plate X. Dash line is plate X. Okay, 3 more minutes, finish up question 5. And then I'm going to cover, I think should be enough time. I want to cover the lens law a little bit more. Do you guys have the answer sheet? Don't have. Okay, answers in the group. Huh? Okay, now last 10 minutes. Keep it quick here. The exercise we can do it later. A little bit more. Lenz's law. Okay, induced EMF opposes the change. Causing it. Okay, let's say this is the coil. Here, from this position, the field, the flux is 20. Okay, I move this one to here. This flux has increased to 100. What does Lenz's law say? If I have a coil here, I move the magnet close to it, the flux will increase. Okay, there's a change in flux. Lenz's law says that every single coil, every single object, they have this nature. What nature? They have this nature to oppose the change of the flux. What does it mean? Okay, we know that the change is from 20 to 100. When I make this change, the coil will oppose it. What does it mean? That means the coil doesn't want it to increase. What is the change I make? I increase from 20 to 100. That is the change I make. But then the coil wants to oppose the change. That means it doesn't want the field to increase. It wants the field to maintain at 20. Okay, that is due to the nature of the coil. It wants to maintain here, just like inertia. Inertia is what? Something that resists the change in motion. If you want to move it, they want to stay at rest. You want to stop it, they want to keep moving. Right? So it is a property that they want to resist the change. So if I increase this one to this one, then what they do? What does the coil do? They will oppose the change by creating a flux. If I increase from 20 to 100, they want to remain 20. What they do? They create a flux in the opposite direction, 80. So you have 100, here 80, comes back 20. Okay, so this coil here, it will create a flux. 80 here, all this, 80. The second I move it close to it, the flux will create the field. It will create by itself. It will create the flux. Because it wants to oppose the change. So 100 minus 80, you get 20. Now, How does the coil create this flux? Flux, you know already, flux is dA. To create flux, it needs to have area and B. It already have area. This is area. It needs to have this B. What is this? This is magnetic flux density. Where does this come from? This comes from current. You have I, you have the B. So to create the flux, the coil will start to order the charges to move. They will give an order to the charge to move. Only when the charge moves, then this flux is created. All right? So all the free electrons in the coil will start moving. The moment you move this one will start moving. Where does it move? Because this one to create the flux in this direction, right? We're going to use our right-hand grid. Right-hand grid, flux in this direction, or field in this direction. Your current has to, like this. Okay? So this coil create the flux here, then it will order its charge to move to the back, like this. So this is the flow of current. This is the flow of current. The current will start to flow, and then this creates a charge. Okay, so Lenz's law. This is the meaning of Lenz's law, and also it explains how a conductor is able to create a flux because of the nature of this one, opposing the change. Now, same thing. If I start here, this magnet here has a flux of 100. Now I pull it away until here. The flux becomes 20. Where is the flux pointing? This one, the flux all pointing to the right, right? So initially it's 100. I pull it away, there's a change. What is the change? Minus 20. The coil doesn't want it to change. What happened? It will create a flux again. It will create a flux in this direction, 80. So after I put it here, 20, it is still 100. Okay? It wants the field, the flux to remain as 100. So when I put it back, it will create 80. Again, it creates the flux in this direction, then the current will flow in this direction. Okay, so if I make this a solenoid, then here is magnet, south and north. Okay, this is the first coil. This is the first coil. Just think of it like multiple turns. If I remove this one like this, the field is in this direction, right? This one, the red one, 80. That means where is your north? Here. The thumb is always pointing to the north, like this. All the current will flow like this. Sorry, this one is towards. Yeah, this one towards. Towards it, it will oppose it. Current will flow like this, and this will become north. If this is north pole, this is south pole. What is happening here? This one is when I pull it away. So like that. And when I pull it away, it creates a flux opposite. So this is the flux, this is the current. Where is north pole? This is north pole. This is south pole. Okay. So whenever I approach it, it will try to repel. Whenever I move away, it will try to attract me back. That is the nature of the coil. Okay, so very easy to remember. Just think of it like, if I want to approach, they don't want. They want to oppose it. If I want to move away, they also want to approach it by changing their polarity to south pole. So this is how the polarity changes if I go like this. Yeah. So that is Lenz's law. right? Not only in the coil, it can be the swinging, the oscillation also. If you allow a conductor to oscillate between the magnet like this. Later in the exercise, we'll do one question like this. This is the magnet, and this is the field. Okay, this one, conductor, oscillate inside the field like this. Every time the conductor oscillates away, moves away, swings away, there is a force pulling it back like this. Okay, that is the field. Okay, this is the conductor. So the field is like going towards the bottom, like this. And I allow this to swing here. When every time it tries to move away, the polarity will be, it will try to attract it. So there will be a force produced here. F. Same here, it tries to move away, there will be a force produced like this. So every time it swings away, there is an attractive force. There is a attractive force. Every time it swings towards the field, there is a repulsive force, just like what we see here. It can happen here, it can happen